So, let us today first discuss the issue of obtaining a starting feasible spanning tree solution to your network flow problem, min cost flow problem. So, here is a problem with 5 nodes, and these numbers indicate your, I should have said somewhere here, these are your BIs. So, node 1 and node 3 are the 2 source points, and nodes 2, 4 and 5 have demands. So, the demands are shown with the negative PIs. Okay. Then these numbers, the first number is the cost and the second number is the upper bound on the arc, on the flow, right. So, there is more than one way always of obtaining a basic feasible solution, starting feasible solution. I will indicate both to you, but we will discuss this one in little more detail, and this is phase 1. So, that means phase 1, right. So, the idea is that you add artificial node to the network and then connect all nodes which have positive supplies to with the arc coming into 6, and all nodes which are your market points, that is 2, 4 and 5, you connect the arc has to go from 6 to that node, right. So, you can see that, and of course, the supply here would be 0. So, therefore, you see this point will then get 8 units, because 5 plus 3 are the total supplies available in the network. So, 8 units will go to 6, and then these 8 units will get redistributed to 2, 4 and 5. So, 2 has the demand of 2, 4 and 5 both have demands of 3 units. So, this is the thing. So, you start with this, and you can just like your phase 1, that you start your basic feasible solution with the artificial arcs. So, here your starting solution 16 x16 is 5, and of course, the cost to these arcs will be 1, just like in phase 1, okay, and the original costs will be all zeros, right. So, what we are saying is that your in phase 1 your C, or okay, I will write out this here, C16 is equal to C36 is equal to C62 equal to 6, C4 equal to C65 is 1, right. All other Cij equal to 0. That means, the original arcs have cost 0, exactly phase 1. So, you just see the correspondence at every step. Okay. So, here this is your this thing, and now we will compute the dual solution. So, quickly you see, you can immediately see that for this arc, for example, for a supply point, it will be W1 minus W6, which is 0, right, W1 minus W6, which should be equal to, the cost here is 1. So, for all the supply points, the dual cost would be 1, and for all these things, for all demand points, it will be minus 1, exactly the same way, right. And so, we begin our simplex network simplex algorithm. So, you can see that start with the node, and I will use the first encountered arc, first beneficial arc encountered as the candidate for coming into the basis. So, if you look at arc 1, 2, what is the cost, the relative cost? The relative cost C12 bar is, see, the arc is 1, 2, right, and the 0, the cost is 0 here. So, C12 is 0. So, this will be minus 1, and then W2, which is this, minus 2, this is less than 0. So, in fact, I do not need to repeat these steps, but just maybe 1 or 2 iterations I will show you. So, therefore, this is an arc for coming into the basis, and so you have to add this arc. The moment you add this arc to your tree, it becomes there is a cycle, and you want to increase the flow. So, the orientation of the cycle is this, right. So, if this is plus delta, this will be minus delta, because the arc is in the opposite direction, and here also it will be minus delta. So, we just look at the upper bounds here. See, for example, delta here cannot be more than 3. So, your choice of delta has to be minimum of 3. Then here the flow on this arc is 2. So, you cannot reduce the flow by more than 2. So, therefore, this will be 2, and here of course, this is 5. So, that is fine, you have this, so this is 2. So, that means the incoming arc 1, 2 comes at a level 2. right, and in place arc 2 6 leaves the basis, right. So, we will do the calculation right here, and I will make this arc basic. So, this will become the updated, this is 3 or okay, before I enter this, remember we have to then update the dual solution, and what the rule, the shortcut we were using was that since arc 6 2 is going to leave the basis, so if you drop this from your original tree, then you see what are you left with? You are left with this one. So, T is, so therefore, and your root node is 6 which belongs to T1. So, T2 just consists of node 2, right, and since C12 bar is minus 2, the dual value here would go up by would get reduced by minus 2, which means your new W2 bar, your new W2 is old minus plus 2, right, minus of minus 2, which is 1. So, therefore, the iteration is very quick. This is simply 1, right. This will remain 1. Well, not now. Well, sorry, yes, it will remain 1 because this was part of T1. So, this is this, and this arc goes. So, this arc goes out of the basis. So, this is your new tree, right. So, one artificial arc has left the basis, right. So, let us compute the relative prices again. So, C24 bar is minus 1, so that is less than 0, minus 2 is less than 0. So, we are I will say that this arc, if it enters the basis, there will be an improvement in the cost, and I am taking the first arc that I get, which is eligible. And so, the orientation of the cycle, you see, if 2 4 has to enter, then the and since the flow has to increase on 2 4, the orientation of the cycle will be like this. So, it will be plus delta here, minus delta, and plus delta, right. And so, yeah, that okay, that yeah, right, fine. So, then delta comes out to be minimum of 313, because you already have 2 units of flow here, and the flow at most can be 3 units on arc 1 2. So, therefore, delta will be minimum of 313, you can see, because actually this is only 2 2. So, I should not have written 3 3, it should be 2 2. Okay. Fine. In any way, the minimum value is not affected. So, this is delta equal to 1, and so flow on arc 1 2 reaches its upper bound. So, once I increase the flow by 1 unit here, then the flow has gone up to 3 units, and so this reaches its upper bound. So, since I have to drop one arc and none of these arcs become the flow does not become 0. So, they will remain basic. 2 4 is becoming basic. So, I will drop 1 2 from the basis. That means, I will make the status of arc 1 2 will change from basic to non basic at its upper bound, right. So, therefore, 1 2 leaves the basis and 2 4 enters. So, when 1 2 leaves the basis in the old tree, you see, if this leaves the basis, then your T 1 is all this, and T 2 is only containing arc node 2, right, and therefore, T 2 is 2. And so, your and since the arc 2 4 is entering, that means P q. So, P belongs to T 2, P belongs to T 2, therefore, you will increase the W 2 prime by the C 24 bar. So, therefore, 1 plus minus 2, because C 24 bar is minus 2. So, for when P is in T 2, then you add the C 24 the relative price of the incoming arc, and if q belongs, then you subtract it. So, it is 1 plus of minus 2, which is minus 1. So, that is the only change in your this thing, and of course, you update the flow. So, I have shown it yeah. So, therefore, the new flow I am showing you here. So, the new basic feasible solution, this is non basic, and this is the current flow. I can something okay. I think originally the flow was 3 here on these 2 arcs. And so, I have probably updated the flow right here also, but in any case this is the current basic feasible solution. So, it is 2 2, and this flow is become 1, arc 2 4 enters the basis at level 1, this becomes non basic, and I have shown you okay, fine. So, now we continue with the okay. So, as I said that I am not using the Danzig's rule for entering variable, for where you choose the most eligible arc. I simply choose the first incoming, and of course, you might say what would be the way to first incoming, and of course, that of course, you may decide whichever way. So, the first arc that you hit as a eligible arc, you can enter it into the basis. So, in the example that I solved in the last lecture, the min cost flow problem, I would like you to update there. I use the Danzig's rule for entering a arc in the basis. So, now try to apply the first eligible arc rule and see if there is a difference in the number of iterations. Of course, one example is not enough, but fine, you might just check for that. Okay. So, now I continue with the one more iteration of phase 1 for the min cost flow problem. So, now C bar 3 4, and of course, you may have noticed by now that arcs for which the tail has value 1 and head has value -1, those are the ones for which the relative price will be -2. You might have discovered that by now. So, C bar 3 4 is equal to -2 is less than 0, and so here again when you give the orientation of the cycle, because flow on 3 4 has to go up. So, this is plus delta, minus delta, and this is minus delta, right. So, here delta will be 2, and here 3 4 the flow can be at most 4 units. So, therefore, minimum of 4 and 2, which is 2. So, therefore, the flow can increase by 2 units on the arc 3 4, and in that case 6 4 will become non-basic, right. And so, here also you can immediately see that when 6 4 is leaving the basis, then your T 2 is 2 4, T 1 is this one, right, 1 6 and 3. So, 2 4, and then 4 belongs to your leaving arc is incoming arc is 3 4. So, Q is 4 and 4 belongs to T 2. So, your why should I write this? This should be W 4 prime. So, W 4 prime which was -1. So, -1, and then this is -2. So, +2 which becomes 1. So, W 4 prime is +1. So, I should update this to 1. Okay. And then the flow has to be updated, that means the flow here will become 2, this will become non-basic, flow here will become 1. So, you will continue, and you see that now you have got rid of one more artificial arc. So, the idea is that you continue with the phase 1 till you have driven out all the artificial variables from the artificial arcs from the basis, and you have a flow vector consisting of the original arcs. In case you have you still have a artificial arc at 0 level, then you again know methods how to enter any of the original arcs in the basis to form a cycle, which can form a cycle with the current consisting current tree consisting of the cycle must contain that artificial arc at 0 level. You do that, and then you can enter, because there will be no change in the flow, since the outgoing arc has 0 flow, right. So, your delta will come out to be 0. So, you know you can handle that part, how to finally obtain a basis. So, now of course, the issue that is left is I have not yet discussed that, and I plan to do that as I promised for bounded variable transportation problem also, and the same thing almost applies here. As I told you, the only difference between a min cost flow problem and a bounded transportation problem is that for the min cost flow problem it is a general network, for bounded transportation it is bipartite. So, I would like to give you sufficient condition for a feasible solution for min cost flow problem. So, this we will discuss once I have talked about the max flow problem, but now here finally, I just want to show you what will be the final solution that you will obtain at the end of phase 1, and then you can begin your phase 2. So, we continue with phase 1, and I want just to show you this is what you will get at the end of phase 1. So, all artificial variables are out of the basis, right. I have written here final solution of phase 2. What I meant is that final solution of phase 1, and now you can begin your phase 2. Okay. So, phase 2 you will put the 0 thing here, or no, so the root node is this. So, you will put your W1 as 0, and then you can immediately compute your 2, 3, 4, 5, the W's corresponding to the other nodes, and you can begin your network simplex algorithm. So, no problem. So, as I was telling you that it is possible that your phase 1 may end with some artificial variables in the basis at 0 level, then you know how to drive them out and get a flow vector consisting of the original set of arcs. Okay. And as I said, it is also important that you should know, you should have sufficient conditions for the solution being for the problem being feasible, and I would like to discuss that in one go when we have talked of the max flow problem. So, now ad hoc methods for obtaining a starting solution. The idea simply is that you just start from your first node, whichever is the supply point, send as much flow as you can along the arcs which are going out of it. Then you go to the next node which has a surplus node, you again from there send it, keeping in mind the upper bound constraints. So, you just like that you can try to satisfy all the demand constraints and use up all the supplies, and then you can reduce the solution that you obtain. That will not necessarily be a basic feasible solution. That means, it will not be a spanning tree. It may have more than m minus 1 arcs, n minus 1. If the number of nodes is n, it may have more than n minus 1 arcs. So, then I will give you a method to reduce the given feasible solution to a basic feasible solution. So, the ad hoc method I will demonstrate through an example, and the idea is that suppose at this node 60 units are available. So, I start with the first arc, the 20 units is the capacity. I will just float 20 units along 1, 2, 20 units here and 20 units here, because the remainder is 20 left here now after from 60. So, I will have 20. So, this is my first set of allocations. Then I go to node 2, and node 2 you see had demand of demand of 15. So, 5 units will be surplus, right. So, the idea is that I will absorb the 15 and then plus 5 will go here, right. Now, look at 20 here, which is coming to node 3. Node 3 has no demand. So, therefore, I will send this 20 to the first arc outgoing from here 20, and so this becomes 25, right. This gets used up. Now, you come to node 4, and node 4 has 10 units available. So, that means the total amount available here becomes this thing. So, I should have used it. So, yeah, right. So, I should give the number here. So, 10 plus 20, 30. 10 I send here, because this is the maximum that you can send along arc 4, 6, and so 30 will go here. Sorry, 20. 20 came from here, 10 were available here. So, then all the 30 get distributed, right. And then I come up at node 3, again this one is absorbed. So, here this is 3, 5, capacity is 20, I send all the flow, all the units available here along the arc 3, 5, and then at 3, 5 you have 10 more units. So, we will send 20 here, because well, okay, why 20 here? I could have sent okay, because this was minus 5. Yeah, okay, well, this is up to you. So, like because capacity here was 30, I could have sent all the 20 here and the 10 here. I could have sent 30 here, and because the demand here is 60. So, I could have done that 30, and then at node 6 5 units got absorbed, but anyway I chose to redistribute it. So, 20, 10. There is another reason, because I want to show you how to reduce this feasible solution to a basic feasible solution, right. Anyway, so it does not matter. So, here then you have 5 units available required. So, from 10, 5 are left, and so along this arc you will send how many? So, let us see what is happening. Yeah, 25 is coming from here, 20 is coming from here, 45, and then 10 came here and 5 were left over, because 5 got demanded. So, 15, so 15 go here, 45 plus 15, 60. So, this is a feasible solution. All this, so ad hoc way you can sit down and program your own way of doing it, how to compute the ad hoc method. By ad hoc method you get a feasible solution. And now, because we want to get rid of the cycles, remember a spanning tree solution will have no cycles present in it. So, we will one by one try to redistribute the flow along the cycles, right. So, if you look at the first cycle here, 1 3 2 1, right. So, I cannot do anything here because the capacity is 20 and the capacity here is also 20, here it is 35, but for increasing the flow here along this cycle I cannot, I will have to increase the flow here also, I cannot do it. So, therefore, for this cycle what I will do is, since both these arcs are at their upper bounds, I'll rename these arcs 1 3, 1 2 and 1 3 as non-basic arcs, non-basic arcs at their upper bounds. Remember, the idea is that I just want to have how many nodes are there? 7. So, I should have 6. I should have 6 arcs which are in my basic, which form my basic tree. So, I'll just put, instead of this I'll put a square to indicate that this is a, and I'll write a broken this thing. So, this is a broken arc to indicate that it's not a part of my basic tree. So, here also this is 20 and this will be broken, right. So, that is it. Now, we want to go look at, so therefore, both these cycles are not there anymore, right. Now, you look at the cycle, or you look at the cycle 2 3 5 7, 2 3 5 7. So, here arc 3 2 has capacity more than what is. So, therefore, if I try to flow delta units here, then this will be plus delta, I can do it, then this will be minus delta and this will be minus delta, right. This way I can redistribute the flow. So, what is the limit for delta? It comes out to be 20, fine. And since the idea is to get rid of as many as many arcs as possible, in the sense that I should only have 7 of them left. So, I will choose delta to be 20, and so both these arcs will go away, right. And so, the flow here will become, oh, but I cannot choose delta to be 20 because this is 35. So, only 15, and here this is 10. So, I can choose delta to be 10 only. So, that means, yes, and once I choose delta to be 10, then this arc will reach its upper bound and I can then call it a non-basic arc, because I am searching for 6 basic arcs which can form my basic feasible solution. So, delta is 10, therefore, this flow becomes 30, right, and this now becomes a non-basic arc. So, this is 35, I will do it this way, and this is a broken arc, right. So, here the flow becomes 10 and here also the flow becomes 10 units. So, this is what, keeping the upper bound constraints and maintaining flow conservation, that will anyway be maintained if I reallocate the flow along cycles. So, then I have this. So, I have managed to get rid of 3 arcs, or at least rename 3 arcs as non-basic, right. Now, you look at this cycle here. So, this cycle, see what is happening is, yes, I can try to increase the flow here. The upper bound here is 40, that is no problem. Then I can reduce the flow here by 10, and what about 5 6? 5 6 also. So, if I increase the flow along this, then it will go plus delta, minus delta and plus delta, right. So, this arc will get removed because delta is 10. See, 5 6 the limit is 30. So, fine, for 3 5 it is 20. So, delta can be 10, and 4 3 there is plenty of scope because the upper bound is 40. So, I can choose delta to be 10, and again you have the choice of either making this non-basic or this non-basic, because this will be non-basic at its upper bound and this will be non-basic at 0 level. So, let us do that, right. So, we will remove this arc goes out, right, and so this will become 30, and this will become 20. Yeah, sorry, no upper bound, this is remains at its. So, this is 20, and here the flow is also 20. but I am leaving it as a basic arc, or I can decide to. So, let us see how many do we have, 1, 2, 3, and I need 3 more. So, therefore, I will have to keep this at a base, because this cycle I have to remove one arc, I have to get rid of that cycle. So, therefore, I could not have made this a non-basic arc also at its upper bound. Okay, fine. So, this is the new thing, and now we look at this cycle. So, 6 to 7, the upper bound is 35, and right. So, I can increase the flow along this direction by delta, then this will be minus delta, and this will be plus delta, and again delta can go up by 10, because the upper limit is 30. Fine. So, this arc will go out, right, it will remain, it will become non-basic, right, and this flow will be 25, and this flow here will be 30. So, you see, if you remove these arcs, then you have 1, 2, 3, 4, 5, 6. 6 arcs, they form your spanning tree, and this gives you a starting feasible solution. Okay. So, this is an ad hoc method, and one can do, but mostly the softwares that are developed for min cost 4 problem, they program phase 1, because it is easier to program it. Here you can see that you will have to use lot of judgment at every point how to do it, though one can probably program this also, but anyway, I just wanted to show you that you can get a starting feasible solution. Then, yeah, so that takes care of your starting feasible solution. The next step is now what you want to talk about is degeneracy. Remember, that was the second issue that we have to tackle here, right? Okay, let me here begin from the very beginning. So, first I will talk about degeneracy in the simplex algorithm, degeneracy and its repercussions in the simplex algorithm. Okay. So, I did talk to you about, so what I gave you first, the Bland's method. And this I think came around, I must have given you the date exactly in my talk when I was talking about the Bland's algorithm, 1976 or 77, or I am not very sure, but anyway, one can check that. So, this was given by Bland, but I should have any discussion on degeneracy would be incomplete without the lexicographic, because that concept still is used, maybe different ramifications of that concept is still there. So, I thought I should talk about the lexicographic method. So, what does lexicographic what does it say? Lexicographic method. Okay. So, the idea here is that you want to make the choice of the outgoing variable unique, right, and of course, one can say maybe you toss a coin, or maybe you can, but it has to be where you show that the particular choice will lead you to a finite number of steps of resolving degeneracy. That means you should not cycle. So, this is what we mean by saying that the choice of the exiting and the incoming variable should be unique in such a way that you can say that the number of degenerate pivots will be finite. I mean, a sequential or successive degenerate pivot should be finite. This is the idea. So, lexicographic was much before Bland came up with this. This was right in the early 60s. It was proposed, and the idea here is, see, I will draw the diagram and then write down the rules. See, what is happening is, you have this right hand side vector, okay, and suppose you choose this variable to enter the basis. So, your ck minus zk is less than 0, and we are saying that this is the most negative. So, our incoming choice, just as Danzig's algorithm said, to choose the most negative one to enter the basis. Then what was happening was that we looked at the positive entries here, right. So, this is the kth column. So, we looked at the positive yij's and then took the ratios. So, therefore, the first step was you took bi by this upon yik, right. So, we took the ratios for where yik is positive, right, and then we said that let me write the index set here. So, we said that let I naught be equal to all I or all R consists of all R such that BR bar upon YRK is minimum of BI bar upon YIK positive. Okay. So, I naught was this. Now, if R was unique, if I naught had only one index in it, which is R, then so if I naught is equal to R, then sorry, here it would mean 1. Then XBR leaves the basis. LEAVES leaves the basis, right. But the problem came when you had more than one index in the set I naught. That means there was a tie. Suppose for this and this there was a tie, right. All three ratios were the same. So, then how do you decide which one exits the basis, right. This is where, and because once you do the pivoting, then on any one, then the remaining two variables will become 0, the new values will be 0, and so you can cycle. So, one wants to avoid that, right. So, therefore, Bland gave you one rule, which was that if you have more than one, then choose that smallest index. That means, out of the 3, if this is the smallest basic variable in terms of its index, then you allow this to leave the basis. So, Bland gave you this rule. Now, before that, the prevalent rule was, see, suppose these m columns, for the identity matrix, right, in the beginning. So, therefore, this initially this was I, that when we started the algorithm, suppose your starting basic feasible solution was an identity matrix, and this will happen if you have slack variables consisting of making up your basis. Then this was the identity matrix, and now, of course, so you have y1 to ym. So, at some intermediate iteration, these are the new columns, right, they have been transformed. So, then they said that suppose, so now you have I naught, you have more than one index here, then you take the corresponding element here and divide by this. So, then you take the ratios for this column from here, right. That means, sorry, first you chose, you took the ratios for the yik is positive, you took the numbers here and took the corresponding ratios, there were ties. Then you take the now the ratio, that means you should form the index set I1 such that I1 consists of R, where now you have YR1, that means the Rth, this thing from here, divided by YRK, right. This is minimum of YI1 upon YRK, right, I belonging to I naught. So, clear, the definition is that for all the indices that are present here, you take those components, corresponding components in the first column here, and then take the ratios from the corresponding yiks, and then again find out the ratios, and then choose the minimum one, right. Now, same rule here again, if this is 1, then xbr leaves the basis, right. Otherwise, you then form I2 with respect to the column y2. So, do the same thing, that means whichever indices are there in I1 for which the ratio is the same, there is a tie. For those ratios, you will choose the y2 column, take the corresponding ratios, and then again find the minimum one. So, this process goes on, right. And why will it end? Because you see, if the things continue to tie, then the process will end for j less than or equal to m. Process will end for okay, I should say for n for ij, where j is less than or equal to m. What I am trying to say here is that taking the ratios for column wise, the process must end much before we reach the mth column. Suppose it does not happen, then what would it mean? That the index set I m has cardinality more than 1. That means, I have not come to a unique choice of deciding which variable to leave the basis. So, this means that any two rows with indices in I m are multiple of each other. That will imply, because you see what is happening is that if index set of I m is more than 1, say suppose R 1 and R 2 are two indices in I m, then what does it mean? That the ratios are the same for all, because I have reached up to here, and so for each of the columns the ratios have been the same. So, y r 1 j upon y r 1 k is y r 2 j upon y r 2 k, right, corresponding to this column I am taking the ratios. So, then j varying from 1 to m, which would imply that y r 1 j is y r 1 k upon y r 2 k, y r 2 j, right, because these numbers are non-zeros, remember, positives. So, therefore, you see, and this is true for j varying from 1 to m, which means that the r 1th row is a multiple of the r 2th row, and these two rows are the rows of B. Remember, because we said that these columns represent the initial our starting basis was here. So, these rows are, but that means here if r 1th row is a multiple of r 2th row, the two rows cannot be linearly independent, but that is not correct, because rows of B are linearly independent. So, therefore, this process of taking the minimum ratio must end much before we reach the mth column, or at most at the mth column. That is when I have a unique choice of deciding which variable should leave the basis, and that is the whole idea, because we said that we want to break the cycling process by making a unique choice of incoming variable and the exiting variable. But as we said that these are all very time consuming things. So, now you see this is fine, this used to work fine, but again you can yourself see that to program this would, and if you have to do this exercise at every iteration, it will be very expensive. Okay. So, that is why Bland came up with his idea, which was very easy to implement. Bland's idea did not require any such calculations. You could very simply implement it. It could be programmed in any software for the simplex algorithm. But then what turned out is, it was noticed when the Bland's algorithm got used, was that the number of iterations became very large, because the long paths of degenerate pivots you could continue to have, though of course you prevented cycling, of course, which is better than having a long set of path of these degenerate pivots. But then same thing, I mean here you had to do many more iterations. Here it was expensive to work out every iteration of the simplex algorithm. Then it turned out that what was said is that because here you do, for when you compute your right hand side, compute the basic feasible solutions, you divide by the determinant of the basis. And so, because of the rounding of errors, so I should write it out somewhere here. Okay. So, the round of errors play a role. Round of errors do not give you exact zeros on the right hand side, right? You'll seldom see zeros here exactly, because of the, because you know that the computers work with finite arithmetic. And so, what was felt was that this will really not happen when you're dealing with a general linear programming problem and solving by the simplex algorithm, because this right hand side will appropriately get perturbed, because you will not get zeros, and so you will not have a degenerate solution, and therefore there will be no cycling. This is the empirical feeling, and this is fine. But there is also, I think, this is a software developed by I think some Canadian people, so which sort of perturbs the right hand side appropriately, so that you don't get degeneracy. See, this is of course a very theoretical and comprehensive method, but as I said, it will be very expensive. So, this program takes care of degeneracy and therefore cycling in the simplex algorithm. Now, for the network simplex algorithm, the story is different, because for the network simplex algorithm, you don't the determinant of the basis is always 1 or minus 1, right. So, therefore, you don't the round of errors are not do not occur there, and your basic feasible solutions will always be plus minus of the BIs, and therefore, the zeros will occur. So, in the network simplex algorithm, degeneracy is a real problem, right. So, we will say in, yeah, this is the last statement I make. This is a network simplex algorithm. In a network simplex algorithm, degeneracy is a real problem. Okay, real problem, I mean that it will occur, because I have not yet talked about the assignment problem or the shortest path problem. I'll show you that, you see, even in the shortest path problem that we discussed, it is not necessary that a shortest path will have n minus 1 arcs in it. It may have fewer than n minus 1. So, you are going to have a basic feasible solution which is degenerate. Similarly, I will sometime mention the assignment problem, which is highly degenerate. So, therefore, in network simplex algorithm, the degeneracy is a real problem, and so we have to tackle it. And so, for the transportation problem, for example, I have mentioned it, that you should try to, I gave you one epsilon perturbation method for handling degeneracy. Then I said you should apply Bland's algorithm also, and you will see that you may end up with more iterations than the epsilon perturbation method, right. So, we have to then combat degeneracy in the network simplex algorithm, and will, because of the structure, again we will be able to give you better methods than Bland or the lexicographic method. So, we discuss that after this. So, Cunningham in 1976, maybe I should give the name here. Cunningham in 1976 came up with the idea of working with strongly feasible basis. So, let me explain what we mean by that. A strongly feasible basis definition, this is a rooted spanning tree such that all arcs with 0 flow are pointing, this is pointing towards the root, pointing towards the root, and all arcs, I mean in the tree span. So, it is a spanning tree, it is a rooted spanning tree, so that all arcs with 0 flow are pointing towards the root, and all arcs at their upper bound are pointing pointing against the pointing in the opposite direction, right. And you can see that. So, I will give you an example what we mean by this. See, this is an example. So, if I call this A and this I call B, then A represents a strongly feasible basis. You see, because here this is an arc which is saturated and it is pointing away from the root. This of course does not come into the definition because it is not saturated and the flow is positive. Similarly, here again this one is saturated, so the arc is pointing away from the root, right. Then here this is okay, this is not saturated. Here the flow is, oh, so this is not, I have to say that this should be this way. So, here this is 0 flow, then it has to be pointing towards the root, and the idea is that another way to define a strongly feasible basis is that from every node of the tree you should be able to send positive flow to the root. And you see that immediately from here, for example, I can send a positive flow of 2 units because you already have 2 units here. So, this flow will get reduced, it is possible to do it. Then from here, because again you have 3 units in this direction, I can send 2 units here, right. Similarly, from here, because this is saturated, I will reduce the flow and I can send 2 units here again along this arc, right. Similarly, from this point onwards, because the flow is 0, upper bound is 3, I can send at most 3 units, and then but here I can send 2 units. So, therefore, from 6 to 1 you can send 2 units. So, A represents, right. So, figure A represents a strongly feasible basis. Yeah, I have not given you the see, the idea is that it is a feasible solution in the sense that the demands and the supplies are met, and after that this is the additional condition we are imposing, right. But figure B does not represent a strongly feasible solution spanning tree, because here you see this arc has 0 flow and it is pointing towards away from 1. So, therefore, from 5 I cannot send any flow to 1. From node 5 I cannot send any positive flow, right. So, an alternate definition is that for a strongly feasible spanning tree, it should be possible to send positive flow from any node to the root node. Okay, so this is an alternate, and which one can very easily check. One can write a small program to always check whether this is this, right. Now, then the second thing is, how do you maintain at every time, because if you have to bring in a base arc into the bases and remove an arc, then so how to maintain, that is the next step, right. How to maintain a strongly feasible basis. How to maintain a strongly feasible basis. So, the idea here is that suppose I will first explain in words. Suppose this is an arc which is coming into the basis, right. So, suppose 7 6 is an arc which has to enter the basis, then and suppose it is at 0 flow, at 0 unit, the flow on the arc 7 6 is 0 currently. So, therefore, you are going to, this will be the orientation of the cycle, and you will increase the flow by delta here, right. Now, this increases delta, then here it will be plus delta, this will be minus delta, this will be plus delta, because it has the same orientation, this will be plus delta, and this will be plus delta, right. So, if this is an incoming arc, then this is what you have. So, now just see, so first of all we define what is called an apex node. So, I will write it down, the definition. The idea is that if this is an arc which is coming into the basis, then from both these nodes, the tail and the head of the incoming arc, you have path up to the you have a path up to the root node. So, if this path meets somewhere before the root node, then that will be the apex node, otherwise root 1 is the apex node. So, we will first, let me make a few definitions here. So, what we say is that suppose, so I will give you the rule for, suppose LK is the incoming arc, and the current flow on it is 0, right. Therefore, the cycle formed has the same orientation as that of the arc LK, right. It has the same orientation. Then let the paths from nodes L and K to the root node meet at a node W. W may be the root node also, right. Then W is called the apex node. W is called the apex node. Okay, it's the apex node, right. And then this rule is simple. So, then determine and suppose now let delta be the amount by which the flow can be allocated along the cycle, or actually reallocated along the cycle, right. So, and you can say, and suppose that Ij and St are the blocking, or maybe are the blocking arcs. There will be more than 2 blocking arcs. Blocking arcs, we mean the arcs which will the arcs which will limit the value of delta, right. So, for example, here the value of delta will be determined by, say, delta would be what, minimum of U76, right, because the flow on this cannot go beyond the upper bound limit. Then here, for example, the flow can go up by 3 units only, right. Then here the flow can decrease by 2 units only. So, I am just writing out like this. Then here the flow cannot increase at all because it is already at its upper bound, so it will be 0. Right. Then here it can go up by 1, and here it can go up by, it can again go up by 0 only. So in this case it is 0, and the blocking arcs are this. So the blocking arcs, right? So therefore in this case the blocking arcs are 1, 2 and 5, 7, because they limit the value of delta, right? The delta cannot be anything positive here. So these are the blocking arcs. So the idea is, so therefore now I have defined for you what are the blocking arcs. Okay, these are the arcs. Which limit flow delta, right. So now what it says is that choose, so the exiting arc, this is the rule finally they are giving, exiting arc, which has to be unique, is, so this is the last blocking arc when the cycle CYCLE the last blocking arc, okay, last blocking arc reached from W, that is the apex node, reach from W to the node we said that the arc that is incoming is LK to the node L. Let me explain. That means it is the last blocking arc. See here what we are saying is that this will be, if you are coming here, so from W, this is your apex node now. So when you are following the path from the apex node to the tail of the incoming arc, then the last blocking arc, that means by this definition this will be the arc. So the flow will not change, that means this will become a basic arc. If you want to make it at 0 level, you want to make it basic, then this will be the exiting arc. Okay. So here this is the last blocking arc. So one can make it more clear here, just to say that exiting arc is the last blocking arc reached from W to the node L, reached from W along the path. Okay, we can say that here I can make it more W along the path, to node L. So it's the last one. If you do it, then what you have it, so the remaining, so the new tree is again strongly feasible. Yes. So I'll show you some more this thing, and of course the question would be, how do you then get a starting strongly feasible solution? The phase 1 tree that you got is a strongly feasible solution. You can check for yourself, okay, because these the artificial variables, the artificial arcs do not have any upper bound limits on them. Okay.